तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Two different kinds of data models now when we are talking about how to design a database system. The first data model that we saw was the entity relationship model, which is especially used for building conceptual schema. So as we have defined, a conceptual schema is something that is meant for human consumption, that is it is meant for communication with end users, so that they can understand what the database designers have really understood about their domain, what kinds of entities exist, what kinds of relationships exist, and so on. But an entity relationship schema is not really the best data model for storing data in a computer. And for storing data, that is the internal schema or the physical schema, it is usually the relational model that is used. And the relational model has in some sense has some kind of common terms with the entity schema, like we have seen the concept of keys, foreign keys, and referential integrity, and so on, which hold both for entity schema and the relational schema. However, the relational schema is mainly meant for the physical schema or the internal schema, while the conceptual schema is meant for the human consumption, while the physical schema is meant for the computer. Now, usually what happens in a database design process is that we use some kind of tools or some kind of case tools to build an ER model or of the information system that we are trying to design. And there are a number of automated techniques by which or number of automated tools which can take a ER representation of a schema and then convert it into a relational schema. However, while this is automatic, this need not always result in the most optimal form of the relational schema. And what do we mean by optimal? We are going to try to formalize this notion today and try to see which kinds of relational schemas are better than which other kinds, and are there some kind of techniques, formal techniques that that I can use, by which without trying to understand the semantics, just given a relational schema, doesn't matter in what context, can I try to optimize it into a fashion that that can help in efficient storage and retrieval of data. So today in this session we are going to look at an important concept of relational database design, namely the idea of functional dependencies. The notion of functional dependencies is fundamental to the design of different normal forms which we are going to see in a relational database schema. So what are functional dependencies? Functional dependencies are a framework for systematic design and optimization of relational schemas. Of course, there are many more non-systematic options for optimization. For example, if we know something extra about the operational domain or the specific database in use, we can always optimize something more than what we can do with the relational with functional dependencies. However, functional dependencies are some kinds of techniques that are database independent and can be used in a formal fashion in order to achieve some level of optimization or some level of efficiency in terms of database design. We are going to see how we can define keys. We have looked at the notion of super keys, primary keys, and so on, how we can define the notion of keys using functional dependencies. In fact, functional dependencies are a more generalization, or is a generalization over the concept of keys, and they are crucial in obtaining the correct normalized schemas when we are trying to design database systems. So let us first define the notion of a functional dependency. Let me first take the definition here, the formal definition here, and try to explain it in informal terms. The definition reads: in any relation R, if there exists a set of attributes A1 to AN, okay, and an attribute B, such that if any tuples in the relation have the same value for A1 to AN, then they also have the same value for B. Okay. So essentially what it means, this is a formal way of saying that this set of attributes A1 to AN uniquely determine the value of B. That means if two or more tuples have the same value of A1 to AN, it is not possible, essentially that means to say, that is they should have the same value of B, they can't have different values of B, because these sets of attributes A1 to AN uniquely determine the value of B. So this is called a functional dependency, and a functional dependency is written as shown in the slide here. It is written as A1, A2, etc. AN, and there is a right arrow to B. So an important thing to note here is that functional dependencies define properties of the schema and not of the tuples in the schema. What does that mean? Essentially this kind of dependency that exists between A1 to AN and this attribute B should be a property of the entire set of tuples that are there in the schema. For example, I might say that the employee number uniquely determines the name of the employee, okay, in any relational database schema. However, we cannot say that let us say the employee name uniquely determines the age of an employee, because there could be two or more employees having the same name but different age. But it could well be possible that there is a certain employee with a very rare name and there is nobody else who has that name, and therefore for this particular employee the name uniquely determines the age, or uniquely determines his or her age. But this is not a property of the schema in itself. This is a property of that particular tuple of this particular employee who has this rare name, so that there is nobody else with that name, therefore we can uniquely identify the person and the age of that person. So when we are talking about functional dependencies, we are talking about properties of the schema which holds for all relations or all tuples in the schema. In any given schema there could be many functional dependencies. Let us say the set of attributes A1 to AN can uniquely define, it is also called uniquely determine B or defines B, and so on. So A1 to AN can uniquely determine B1 or B2 or B3 until Bm. So this is written as shown in the slide here, that is A1 to AN and right arrow B1 to Bm. Okay. Now why is this called a functional dependency? What is so functional about functional dependencies? If you are familiar with the mathematical notion of a function, which is a special kind of mapping or a special kind of relation between sets, you can see here that the notation that is used, for example A1 to AN, or uniquely determining some attribute B, is precisely the notation used for a function. It basically determines, because A1 to AN uniquely determines a particular attribute B, it acts as a mapping, or it acts as a function which maps this set of attributes A1 to AN uniquely to each B that it defines. This precisely acts as the mathematical notion of a function. However, there need not be any computation that determines this unique definition. For example, the employee number may uniquely determine name. However, just given the employee number, I mean I won't be able to compute, I won't be able to determine what is the name. It's just that each employee number has a different or identifies an employee with a different name or identifies uniquely each employee. However, it is not possible to determine what is the name of the employee given just the employee number. We still have to access the database to do that. So let us revisit the notion of keys now when we say functional dependencies. As you might have noticed, the notion of functional dependency is actually a generalization over the notion of keys. That is, in the previous slide here, if a1 to an uniquely determined the set of all attributes which form the relation, let us say a1 to an combined with b1 to bm forms the entire relation, then we see that a1 to an is nothing but a key for this relation, that is for the entire relation comprising of a1 to an and b1 to bm. And similarly, minimal super keys or candidate keys can be defined analogously. Let us take some examples now. Consider a relation of the form that is shown in the slide here. The slide shows a relation called movies, which has the following set of attributes. It has title, year, length, film type, studio and star. So going by the standard definitions of what is a movie and what are titles and what is the year of its release, the length of the movie and so on, we can from common sense reasoning identify some kinds of functional dependencies. For example, given the title of a movie and the year in which it was released, I can probably uniquely determine what is the length of that movie. Okay? And similarly, given there is a bug in the second slide here, second functional dependency here, given a title and the year of release of a particular movie, I can probably determine what is the film type. Given a movie of a particular type, of a particular name and the year in which it was released, I can probably say, well, this is an art movie, this is a commercial movie, this is social documentary, this is a comedy, tragedy, whatever. Similarly, I can probably also say a title comma year uniquely determines say film studio. Okay? However, title comma year may not uniquely determine the star, that is the actors who star in that movie, because there could be more than one actor who have starred in that movie, and you cannot uniquely determine, given the title and the year, you cannot uniquely say, well, this is the movie star who acted in that movie, because it need not be complete. There could be other stars as well. Okay? So let us see what kinds of properties we can identify about functional dependencies and what we can do with these properties. Note that if in any given relation R, if I have a functional dependency of the form A to B, okay, where A is a set of attributes, now I am using the term A, that is without a subscript, to determine actually a set of attributes. Okay, so if the set of attributes A defines a set of attributes B, and the set of attributes B uniquely define another set of attributes C, then we can easily identify the functional dependency saying A also defines C. So there is an example here. If the employee number is given in such a way that it also defines the job of the employee, let us say all employees who do supplies work are given numbers between 100 to 200, and all employees who do administrative works are a clerical job is given numbers between 201 to 300 and so on. Okay? So employee number suppose uniquely defines job, and let us say job also uniquely defines salary, that is every employee of a particular job has the same salary. Then we can easily say that the employee number actually defines salary, that is given just the employee number, I will be able to determine what is the salary for that employee. Some more definitions. Suppose we have two sets of functional dependencies, A and B. Okay? Now again A and B are sets here, okay, and we have two sets of functional dependencies A and B, and that is A defining B and C defining D. Now these functional dependencies are said to be equivalent if the set of all relations that satisfy the first functional dependency is the same as the set of all relations satisfying the second functional dependencies. Okay. Similarly, a small generalization over this definition, we say that a functional dependency S follows another FD called T if the set of all relation instances satisfying T also satisfies S. Okay. So we will take up examples here. The follows property of a functional dependency is extremely important, by which we will be able to compute what is called as the closure of a functional dependencies. That is, suppose I give some kind of functional dependency saying A defines B, what else can I say about that? What else can I infer from this functional dependencies is what we are going to take up. Before we move on to inferring functional dependencies, we need to complete a few more definitions. The next definition that we are going to take up is the notion of a trivial functional dependency. Okay. Now a trivial functional dependency may look of course trivial, but it is quite important when we are trying to define let us say normal forms. Now have a look at the example in this slide here. The slide shows a functional dependency of the form title comma year defines title, which is obviously true. Every attribute defines itself, that is every attribute uniquely identifies itself. Therefore any functional dependency in which the right hand side is contained within the left hand side, that is the antecedent or the right hand side of a rule is a subset of the left hand side of a rule, then it is said to be a trivial functional dependency. If there is at least one element in the right hand side which is not part of the left hand side, then it is called a non-trivial functional dependency. And usually we are interested in what are called as completely non-trivial functional dependencies, which says that none of the elements in the right hand side belong to the left hand side. We will see that this notion of triviality is not so simple, because essentially when there are circular dependencies it becomes quite tricky to handle functional dependencies which are or remove triviality from functional dependencies. We now come to an important aspect of functional dependencies, the notion of closure of FDs. What do we intuitively understand by the term closure? If you are familiar with the notion of closure in say discrete mathematics, you would probably recall the definition that the closure, we say that a particular algebra is closed when I say when I take certain elements from or certain operands from a set of from a set that defines the universe, and then perform an operator, that is perform some kind of a function on these operands, and the result of this function also goes back into this set. For example, if I take two integers and add them, the result is again an integer. If I take two integers and subtract them, the result is again an integer. Now this is what is called as closure, that is I take certain operands or take certain elements from a universe, perform a function on them, and the result of that function also belongs to the same universe. Okay. So let us define the function the notion of closure on functional dependencies in an analogous fashion. The closure of functional dependencies defined by A, that is A is a set of attributes in any given relation R, is the set of all attributes that are eventually defined by A. That is how we can eventually define or uniquely determine what all attributes can be uniquely determined eventually by A. For example, let in a given relation let the set of attributes A uniquely define a set of attributes B. Similarly, let the set of attributes B uniquely define two other sets of attributes C and D. Now let the combined sets of attributes B and D uniquely determine another set of attributes called C. Then we say that the closure of A contains all of these attributes, that is A union B union C union D union E, that is all of them. And actually because all of these attributes can be eventually defined from A. From A we can eventually define B, from B we can uniquely define D, and combining B and D we can uniquely define E. So all of these attributes contained in all of these sets can be eventually uniquely defined by A. What about elements that lie within A? Can they be uniquely defined by A? The answer is yes. This is because of the trivial property of functional dependencies, that is every attribute in A uniquely defines itself, which is the triviality rule. However, closure also just A union B union C union D union E that is shown in this slide does not complete the closure of A. If for example there is a subset of A or subset of any element of closure of A, okay, and if that subset of attributes defines some other sets of attributes F such that F is not part of the closure of A, then we also add F to the closure of A. Okay. So let us first look at an algorithm by which we can compute the closure of functional dependencies. Then we look at a few examples of closures. So given a relation R and a set of attributes A, how do we compute closure of A? So initially we start with the set saying the closure of A equal to A, that is equal to all elements of A. This is true because of the trivial functional dependencies. Every element of A trivially defines itself. Now for every A prime that is a subset of A, if there exists a functional dependency of the form A prime defines B and B does not belong to A, that is B is a set of attributes which does not belong to A for as of now, then just add B to the set of elements in the closure of A, and repeat step 2 until no more attributes can be added to closure of A. Okay. So the closure of a set of attributes A is also denoted by A with a superscript of plus, that is A plus. And also note that suppose we run this algorithm and A plus contains the set of all attributes of R. What can we say about the set of elements in A? A is of course a super key of R, because using A we can eventually uniquely define all elements of R. So we now come to the next property of functional dependencies, the notion of inferring functional dependencies or following, that is how do we find out functional dependencies which follow from one another. Given a set of functional dependencies and given no more knowledge about the domain in which a relation exists, what can we infer about any more functional dependencies that exist in R? Okay. So we have already seen one rule for inferring, which is the transitivity rule, which we will revisit again now. But before that, note another rule that is shown here. Suppose A, B, C and D are sets of attributes of R such that the following functional dependencies exist, that is A uniquely defines B, B defines C and C defines D. Okay. Now based on the closure property and transitivity, we can easily say that A defines D. Okay. However, there could be some elements of D which are actually contained in A. Okay. That is D need not be completely disjoint from A. So let D subscript A, that is dA, be the set of all attributes in D such that they belong to A, that is they are actually a subset of A. Now take away these attributes, that is let D prime be defined as D minus dA, that is shown in the slide here. Once we do this, we see that we have actually inferred a non-trivial functional dependency. Okay. That is A defines D prime. That is we started by saying that because of the transitivity rule, A defines D. However, there is some triviality that is there in this definition, and once we remove that triviality, we have actually encountered or we have actually inferred a new functional dependency which is non-trivial, that is which is of the form A defines D prime. So, functional dependencies which are specified or which are given to begin with are called stated functional dependencies, and FDs which are derived are called inferred functional dependencies. Now, given a set of relation, suppose we have a set of functional dependencies that are stated, this set of functional dependencies is called the basis of the relation. For example, in the movie relation that we saw, where a movie is defined by title, year, film type, star and so on, the functional dependencies that title and year define the length of a movie was given. Similarly, the title and year defined the film type was also given. So, all these functional dependencies that are given are called the basis of the relation. Now, if the basis of functional dependencies are such that no subset of this basis is also a basis, that is none of these functional dependencies that form the basis can be derived from one another, then it is said to be a minimal basis for the relation. So, how do we go about inferring functional dependencies, that is computing the closure or getting inferred functional dependencies and so on? How do we go about inferring functional dependencies given a basis, that is given a set of functional dependencies? For this, there are a set of axioms or a set of rules that define how functional dependencies behave. These are called Armstrong's axiom, which are quite useful when we are talking about properties of functional dependencies. The first property is that the notion of reflexivity, which is like saying which is easily obvious based on the triviality rule. That is, if a set of attributes B is a subset of the attributes A, then A functionally defines B. For example, theatre and year, or rather the title and year of a movie functionally defines title. That is, if I have a set of attributes, these sets of attributes functionally define every possible subset of these attributes. Okay. Similarly, the second rule is that of augmentation. That is, if I know that there exists a functional dependency of the form A defines B, that is theatre comma year defines length, then I can add a set of attributes to both sides of the functional dependencies without violating the dependency. For example, I can say that if title and year of a movie determines the length of the movie, then I can add an attribute called star or studio to both sides of the functional dependencies without altering the semantics. That is, I can say title, year and studio of a movie uniquely determines the studio and the length of the movie. Okay. Also note that I need not add studio to the right hand side because it forms a triviality rule, that is there is some triviality that entails from adding the same attribute in both sides. I can as well add I can just add a new attribute just to the left hand side and still the functional dependency holds. Take the same example again. Suppose I say title and year uniquely determines the length of a movie, then I can as well say that the title of the movie, the year of the movie and the studio in which the movie was shot uniquely determines the length of the movie, which is fine, because adding new information to some set of attributes that uniquely determine something does not alter the dependency. Similarly, the last rule is that of transitivity, which we have already seen. That is, if A uniquely defines B and B uniquely defines C, then we can infer that A defines C. The next concept that we learn here is the notion of projecting functional dependencies. What happens if I compute a project operation on a relation? You know what a project operation is in standard relational algebra. A project operation takes certain columns or certain attributes of a relation and produces a new relation out of these attributes. that means it actually throws away certain attributes from the original relation. Okay. Now suppose let R be a relation and f of R be the set of all functional dependencies in R. Now suppose I project another relation S from this new relation R by throwing away certain attributes. Now what can we say about f of S? What kinds of functional dependencies exist in f of S? Obviously for example, if I say that from the movie relation, if I throw away the year attribute of this relation, then obviously I cannot have the functional dependencies which says title comma year uniquely determines length, because the year does not exist in the new relation at all. Therefore at this point at the first step we can say that the functional dependencies in the new relation S should satisfy the following properties. What are these properties? Firstly, they should follow from the functional dependencies in R, that is we should be able to infer them from the functional dependencies that existed in the earlier relation. Secondly, and which is also quite obvious, that they should involve only attributes of S. Obviously they cannot involve attributes of R which do not exist in S. A functional dependency only has to involve attributes that exist in the current relation. So how do we compute the functional dependencies on a projection? Now consider this this example. Rather than going through a formal set of rules, let me explain it by an example. Now given a relation R containing the following attributes A, B, C and D, and let us say the following functional dependencies, that is A defines B, B defines C and C defines D. Now suppose S is projected from R and B is thrown away from R in getting S. Okay. So S has just 3 attributes A, C and D. Now what should be f of S? That is, what should be the set of functional dependencies that lie in S? Obviously we cannot have A defines B, because B does not exist at all in this relation, and we also cannot have B defines C because again B does not exist in this relation. So but can we say anything else about these dependencies? Okay. Now going back to R, let us see what happens when we compute the closure of A. Let us compute the closures of each attributes. Okay. So I have not included the trivial functional dependencies in computing the closures. That is, firstly we start from A defines A, obviously. Then we have a given rule which says A define B, a basis rule, from which we can infer that A defines C, because there is another basis rule which says B defines C, and from which we can still infer A defines D, because there is another basis rule called C defines D. Okay. So in R the closure of A is A defines B, A defines C and A defines D. In S all we need to do is take away all this or throw away all these functional dependencies that contain attributes which do not exist in S. So here A defines B is one such attribute, is one such functional dependencies. It contains B which does not which is not part of S. Therefore the set of the closure of A in S is essentially A defines C and A defines D, or ACD. Okay. Similarly the closure of C in S is C defines D. Okay. That is C comma D in this case, and the closure of D is just D. Okay. Now since the closure of A contains all attributes of S, that is A, C and D, we do not need to compute any more closures. That is we do not need to compute the closures of AC or AD or ACD, because we already have all attributes of A. We already know how to uniquely determine each attribute of A. Okay. Therefore the functional dependencies that exist in S are A defines C, A defines D and C defines D, and of course there are trivial functional dependencies like D defines D and C defines C and A defines A, which are not shown as part of this set here. Okay. So a simple way to compute the closure or compute functional dependencies in in a projection is to first compute the closure of the set of all functional dependencies in the original relation, and then throw away everything which contains attributes that do not belong to the new relation. So what is the use of all these functional dependencies and closure and transitivity and axioms and so on? These sets of underpinnings are used for normalizing or optimizing relational schemas for better performance. What do we mean by optimizing, or what are we optimizing against? What is the property that we are trying to remove? What is the undesirable property that we are trying to remove? This undesirable property is the property of redundancies in relational schemas. If a relational schema is badly designed, then it is going to contain several redundant information which result in a number of anomalies. What are these kinds of anomalies and what kinds of redundancies are these? Let us have a look at them. Redundancy of course means that some kind of information is repeated across different tuples. The same information saying the title is this one, or the year is this one, or the star is that one, and so on. So if the same information is repeated across several different tuples, then we encounter two kinds of anomalies. What are these anomalies? The first anomaly is the notion is that of updation. Suppose I need to update a data element using let us say the update clause of SQL. I cannot update in just one tuple, especially if this particular information is repeated across several different tuples. If the title of a movie is repeated across several different tuples in the database, and later on I see that the title of the movie is entered incorrectly, there is a spelling mistake. Okay. So I need to change the title of the movie in every tuple there in which it occurs. Similarly, the notion of deletion anomalies. Suppose I delete a tuple which suppose I need to delete a tuple about a particular movie given a particular title. I need to delete all tuples which contain this title in its as its attribute. So I need to essentially search the entire database and delete it in several different places, otherwise it again creates anomalies. So how do we design relational schemas so that we can remove redundancies and remove these kinds of anomalies? Now have a look at the movie relation once again. The movie relation has the following attributes, that is title, year, length, studio, and star. And we also have the functional dependencies which says title and year uniquely determine length, and title and year of a movie uniquely determine the studio in which the movie was shot. However, title and year does not uniquely determine star, because there could be more than one actors who have starred in the movie. Okay. Therefore, for every actor who has starred in this particular movie, you have to repeat the information of length and studio across these tuples. Let us say some movie has 2 or 3 different actors, say Shah Rukh Khan, Hrithik Roshan, or whatever. Okay. Now in a given movie, let us say some movie XYZ that is shot in the same year in the same studio and has the same length, it's only the last field, the star, which changes from say Shah Rukh Khan to Hrithik Roshan and whatever. So so for each actor who has starred in the movie, I need to repeat all the other information that forms part of this tuple, which is what is the notion of redundancy. And suppose after doing all this, I find that I have entered the length of this movie incorrectly, and I need to change the length of the movie. I need to change it in all of these different tuples where this is stored. And similarly, the problem of deletion. So anomalies are removed from a relation by the process of decomposition. Now what is meant by decomposition? Given a relation R containing a set of attributes A, you decompose the set of relations into 2 different relations S and T such that the sets of attributes of S and T are subsets of the attributes of A, and there are no anomalies in S and T. Okay. Now, a decomposition that does not contain any anomalies is said to be in what is called as Boyce-Codd normal form, or it is also abbreviated as BCNF. So, a BCNF has the following property. Suppose given a relation R with a set of attributes A, it is said to be in BCNF if there is a non-trivial, note the emphasis on the word non-trivial here, if there is any non-trivial functional dependency of the form A prime defines A double prime, that means A double prime is not a subset of A prime. Okay. So, if such a non-trivial functional dependency exists, then it means that A prime is a super key of R. That is, there is no functional dependency of the form A prime defines A double prime in which A prime is not the key. If that is the case, then the relation is not said to be in BCNF. So, we will take up examples of this once we complete the notion of decomposition into BCNF, and when it becomes more clearer. Now, how do we decompose a relation such that it forms or it becomes compliant to BCNF? Okay. Now, suppose in a given relation R, let there be a functional dependency of the form A prime defines A double prime which violates BCNF. What do we mean by violating BCNF? It means that A prime defines A double prime is firstly non-trivial, that is A double prime is not a subset of A prime, and A prime is not the super key of R, that is it is some other sets of attributes. Now, in order to bring R into BCNF, we decompose R as follows. First, take the set of all attributes that are defined by A prime. Okay. Now, A prime defines A double prime, it may define something else, and so on. Now, let B be the set of all attributes that lie in the right hand side of any functional dependencies that are defined by A prime. Now, remove the set of all attributes A prime along with B and form a separate relation, and retain the remaining set of attributes along with A prime to form the other part of the decomposed relation R. Let us have an example which makes this very clear. Consider the movies example once again. Let us have a look at this relation movies having the following attributes: title, year, length, studio, and star. Now, here the following functional dependency holds, that is title and year uniquely determines length, title and year uniquely determines studio, and title and year uniquely determines it does not determine star actually. So, this is actually a BCNF violating functional dependency, because title and year obviously cannot be the key for this relation because it does not uniquely determine star. Okay. So, title and year is not a super key as the star attribute is not in the closure of title and year. So, to decompose this relation, just remove title and year along with length and studio. Okay. So there is no star here, just remove title and year along with length and studio that they define and put them in a separate relation, and retain title and year along with star to form the other relation. Therefore, we get two kinds of relations, that is movies is divided into title, year, length, and studio, because title and year define length and title and year define studio. So, we have separated them from movies, and whatever is left out, that is star, is combined with A prime, which is title and year, and retained as it is. So movies 1 and movies 2 are decomposed forms of movies. And it is also easy to verify that movies 1 and movies 2 are BCNF compliant. There is one property of BCNF relations, the notion of two attribute relations. Suppose I have any relation that has just two attributes, we do not need to do anything, it is always BCNF compliant. How do we ensure, or how do we prove that a two attribute relation is always BCNF compliant? Consider these 4 cases. Let us say there is a relation R which contains just two attributes A and B. Okay. Now, there are 4 possible scenarios. The first one is there is no functional dependencies between A and B. that is there exists no non-trivial functional dependencies, only trivial functional dependencies are there. A defines A and B defines B, in which case R is definitely in BCNF. Okay. Secondly, there is a non-trivial functional dependency, that is R defines A defines B, but there is no functional dependency of the form B defines A, which is also no problem because in this case A becomes the key, because there are just two attributes, and A is defining B and B is not defining A. So A is the key of the relation, and the relation is in BCNF. Similarly, if B defines A and A does not define B, then B becomes the key. And suppose A defines B and B defines A, which is also no problem, because both A and B are keys, and we can both A and B are candidate keys, and we can use one of them as our super key or the primary key, which is fine, and the relation is also in BCNF. We now come to another form of normalization, which is called the third normal form of a relation. The third normal form is useful because in some cases it is not possible to decompose the relation such that the decomposed relations are BCNF compliant. It is not possible to decompose without losing some information. Now what is let us understand this by an example. Now consider another relation of the form which is shown in the slide here. Let us say we have a relation called drama, okay, and it has the attributes title, theatre and city. That is there is a particular drama troupe that is performing a drama having a particular title in a particular city and in a particular theatre in the city. Okay. So therefore we can identify the following functional dependencies. The first one is title and city. The title and of the drama and the city in which it is being played will probably determine the theatre as well. Okay. So we can say that in this drama played in this city is being played in this theatre only. Okay. Suppose there exists a functional dependency of this form. Okay. And let us also assume for the sake of argument in this case that given the name of a theatre, we can uniquely identify where that theatre is. Given the name of a drama theatre, let us say something like Kala Mandira or Guru Nanak Bhavan or whatever, some kind of theatre name, we immediately know which city in which contains the theatre. Okay. Now FD2 violates BCNF, as you can see here, because theatre is uniquely defining city, but theatre is not the key. In fact, title and city form the key. Title and city define theatre. So given a title, drama title and a city, we can identify theatre. Therefore this is a BCNF violation in violating FD. However, based on the decomposition rule, if we decompose drama into two relations, title comma theatre and theatre comma city, based on this rule here, because theatre defines city. Okay. Now based on this rule, if we decompose drama like this into drama 1 and drama 2, it will actually be incorrect. Why? Because once we perform the join, when we decompose relations and we join back the relations, we should retain all the properties of the original relation. Now when we perform the join between drama 1 and drama 2, then the key constraint will no longer hold. Let us look at this by an example. Let us say drama 1 contains title and theatre entries like this. There is a particular drama with a title, say Yugant, and it is in a particular theatre. Now there is another drama with a different title but in the same theatre, maybe at some other time. Okay. Now this theatre uniquely identifies city. Let us say given a theatre name, I can uniquely identify city. Now if I perform a natural join between theatre that is drama 1 and drama 2 based on the attribute theatre, what are we going to get? We will get a table like this, that is a title, theatre, city, and title, theatre, city. Now if you see given a title and a theatre, there is no unique title and city is no longer the key. That is we do not know, we can have we can have possibly different let us say we can possibly have different sets of attributes that are defined by the same title and city combination. Okay. So it does not uniquely determine the title, that is theatre and city does not uniquely determine the title of the drama. Such dependencies or such discrepancies occur because of a particular property, and which is what we are going to see in this slide here. Okay. So we are going to define the notion of third normal form, which is essentially a relaxation of the second normal of the rather the BCNF or the Boyce-Codd normal form assumption. What is the relaxation that we are doing here? If we notice in the BCNF violating constraint, that is theatre defines city, the right hand side of the relation, that is right hand side of the functional dependency called city, is actually part of the primary key, that is title and city was the primary key. Okay. So in order to accommodate such cases, we use a third normal form assumption, which says that any relation R is said to be in third normal form if there exists any non-trivial FD of the form A defines B. Either A is a super key, which was all the condition we needed for BCNF, and here we have an extra condition which says, or B is a member of some key. Okay. So an attribute that is a member of a key is called a prime attribute. So therefore either B should be a prime attribute or A should be a super key, which is what makes the relation into a third normal form relation. We shall not be going into details of how to prove properties of third normal form relations. However, we will suffice it to note that it is a slightly general form of the BCNF or the Boyce-Codd normal form. Let us quickly visit the last kinds of dependencies and the next normal form that results from it, which is known as the multi-valued dependencies. Now even in BCNF, BCNF is a strict form of decomposition. So even in BCNF we have not fully removed all possible redundancies. Consider this following example here. The slide shows a example relation called drama, which has the following attributes: title, theatre, director and genre of the drama. Okay. And we note that drama is in BCNF because let us say title is the key. Okay. Let us say each drama is played in precisely one theatre. Okay. For the sake of argument, therefore title uniquely determines theatre and director and the genre of the drama. Okay. However, it may well be possible that a given title may be classified into two or more genres. That is, a given drama could be classified as comedy, and it could also be classified as a social commentary. Okay. Now because it is classified as under two or more categories, there exists what is called as this one-to-many relationship between title and genre. Okay. So every time we identify the set of all comedy dramas, the theatre and director has to be repeated. Similarly, every time we identify social commentaries, the theatre and director has to be repeated because it is the same drama. So this is what is called as a multi-valued dependencies. Now what is a multi-valued dependency in a more formal fashion? Now suppose in a given relation A, there is a non-trivial functional dependency of the form A prime defines B. Okay. And suppose A prime is also a key because it is in BCNF. Now suppose if B is completely independent of all other attributes of the relation, then we say that there is a multi-valued dependency. In this case, the attribute theatre and director are completely independent of the category or the genre of the drama. It has no relationship between a theatre may play any kinds of drama and a director may direct any kinds of drama himself. So it is completely independent of that. So we say that there is a multi-valued dependency. Okay. So we define the notion of a non-trivial multi-valued dependency in order to remove them. Okay. So, firstly, what is the notion of a non-trivial multivalued dependency? A multivalued dependency of the form A prime defines B is non-trivial if B is not a subset of A prime, which is the non-trivial property for BCNF as well, and there exists certain other attributes in addition to A prime and B, that is A prime union B is a proper subset of A, the set of all attributes, that is there exists some more attributes in addition to B. So, a relation R of A is said to be in fourth normal form if for every non-trivial functional dependency of this form, that is A multivalued dependency B, A prime is the super key. So, we shall not be going into more details of the fourth normal form, and for this session we will suffice it to say that fourth normal form is an even more stringent criterion for removing duplicates or removing redundancy in relations. So, essentially the normal forms can be categorized like this. Third normal form is the most lenient among the three, and next is BCNF, and finally the most stringent is the fourth normal form. So, if any relation that is compliant to fourth normal form is automatically compliant to BCNF, which is in turn automatically compliant to third normal form. So, we now come to the end of this session, and let us briefly summarize what all we have studied here. So, we studied the notion of functional dependencies, which is a generalization over keys, and properties of functional dependencies like transitivity, reflexivity and augmentation, etc. We also saw the notions of trivial and non-trivial functional dependencies and how they affect BCNF, and how we can decompose relations into BCNF so that we can remove redundancies. However, we see that not all relations can be decomposed into BCNF without losing information, because of which we also need the concept of a third normal form. And we finally saw the notion of multivalued dependencies, which can remove redundancies that exist in BCNF, and the fourth normal form which removes multivalued dependencies. So, that brings us to the end of this session.